So today we have Mathilde from Inria and FAIR. She is a PhD student there, and we are doing a presentation on SwAV.
Yeah, thank you so much. So hello everyone, and it's really my pleasure to be here to present our latest work, SwAV. And yeah, thank you again, Anania and Will, for hosting me. So I will be talking about SwAV, which is a method for self-supervised learning of image features. So here's a brief plan of what I'm going to cover during this presentation. So first I will present the problem of self-supervised learning. Then I will give a brief overview of some of the related works that are tackling this problem. Then I will present our method, SwAV, and finally I will show some of our results. So what is self-supervised learning of image features? So as you may know, for some years now, a typical setting to solve an image recognition task has relied on two stages. The first one is the pre-training of a CNN on a large-scale dataset, so typically ImageNet. And then the second stage is to use those representation to solve a target task with transfer learning. And here the idea is that the better the pre-training, so the better the learned representation, then the better the performance on the transfer task. So this process relies heavily on the use of ImageNet, a large fully annotated dataset that has been expensive to build. And in this work, and the goal of self-supervised learning is to replace this supervised pre-training by unsupervised pre-training. So it means that we want to learn useful representations that are likely to transfer well to downstream tasks, but without using any annotation. And intuitively, we see that there are some similarities, some similar patterns between the different images of a dataset. So it should be possible to leverage this signal in order to learn representation.
So Mathilde, do you have any intuition as to what better, like how the representations can improve or change over just using supervised pre-training?
So first of all, the goal is not necessarily to beat supervised pre-training, but it's just that self-supervised learning is more practical because you do not need annotation. So you can use pre-training in areas where you cannot have annotation or annotations are too expensive, such as medical images, for example. And then maybe there is the hope that unsupervised pre-training can outperform supervised pre-training if, for example, the labels are noisy, or for example, in ImageNet, you have images where you have the label banana, but in the image, you have an apple and a banana. So like what I mean is that the labels are not perfect, and maybe you can do something better without using them. But the first motivation is not necessarily to beat supervised pre-training, but just to be able to learn representations without requiring labels.
Yeah, that makes sense. I mean, that's a good point you bring up. I feel like I always think about labels as like adding a human bias, which may not be necessarily true, right?
Yes, definitely. So now we'll give a brief overview of some of the works that are tackling this problem. So one sub-area of self-supervised learning is what we can call handcrafted pretext task. So here the idea is that we want to design a pretext task, and the hope is that if the network is good at solving this task, it would have acquired a good understanding of the scene and objects present in the images. And here the idea is that for the pretext task does not require labels. So for example, we can think of colorization. So here to train the network, you don't need humans to give labels because the labels, the targets are just the RGB information and it comes for free in the images. And here you hope that if the network can solve this task, it would have learned something about segmentation or something in that sort. Then another area of self-supervised learning is contrastive instance learning. And contrastive learning has attracted a lot of attention recently because of its very good performance on the standard benchmark. And so here the idea is that each image in the dataset constitutes its own class, and then the class is augmented with different distortion and data augmentation of the image. There is also another kind of approaches for self-supervised learning, which is clustering. And here, what we do is that we want to mine clusters, so visually coherent clusters in the dataset, And then we use those clusters as pseudo-labels, as pseudo-assignment for the data set, and then the network is trained to predict these pseudo-labels. And of course, there are many other approaches, and there are also other ways to categorize these approaches. But in this presentation, I will focus mainly on clustering and contrastive learning. Let me give you more details about clustering-based approaches. So here we have a large database and a ContNet. And what we do is that we take the representation given by the CNN for the entire dataset, and then we simply cluster this representation with k-mean clustering. And this gives pseudo-labels that we use to train the network. So here we're doing like simultaneously clustering and representation learning. And one of the ideas of this work is that at the beginning, the first clustering is going to be bad because it is based on a randomly initialized network, but it's not completely random either. And so by training on this bad but not random clustering, the weights are going to improve slightly. And so the next clustering will be also slightly better. So it means that both the clustering and the representation learning are going to improve one another. Here are some examples of clustering-based approaches. So like 2 years ago, my team and I proposed a method called deep cluster. And then last year was published a method called SILA, which like is more principled than deep cluster because they use the same objective for clustering and representation learning. So it increases the stability. And finally, in our SwAV paper, we proposed an improvement of deep cluster, which we call deep cluster V2, where we like perform explicit comparison between the feature representation and the cluster centroids. So it removes the need of learning this final classification layer that changes at every epoch. And so doing like a direct comparison between the centroids and the features improves the stability of training and the performance. So that was for clustering-based approaches. And now I'm going to like present briefly the contrastive learning approaches. So here we're looking at the unit sphere in the feature space of, so for example, the output of a ResNet 50. And this is the feature representation of a patch of an image of a dog, which we call the XI. And here what we do is that we take another patch from the same image and we look at its feature representation. And these two images form what we call a positive pair. And the goal of contrastive learning is to make this positive pair close, but close compared to what? Close compared to negative pairs formed by the anchor, so XI, and features from the other images of the dataset, which are here represented in red. And so intuitively, the network has to pick the positive example out of a pool of negatives. And so since computing all the pairwise comparison on a large dataset is not practical, most implementations approximate the loss by reducing the number of comparisons to a random subset of images during training. And so the different implementations, they differ in the way the negatives are provided. So for example, in NPID, which was published 2 years ago, the negatives come from a memory bank, which is composed of the feature representation from the previous epoch. In MOCO, which was published last year, the negatives comes from the previous batches through a dedicated slow network. And more recently, SimCLR proposed to take the negative directly in the batch. So it's much simpler, but it requires large batches to have enough negatives. So now that we have presented in more details contrastive and clustering-based approaches, we can draw a table of pros and cons of these approaches. So for contrastive approach, I talk about SimCLR. And for the clustering approaches, I talk mainly about deep cluster V2. So these methods have different pros and cons. And contrastive learning scales easily with the dataset size because it is an online method. Everything happens at the batch level, but it needs a lot of epochs to reach convergence. So it is because it approximates a learning objective that relies on direct feature comparison between the features from the entire dataset. And so on the other hand, clustering does not scale well with the dataset size. And for example, for like very large scale training, so billion scale trainings, Facebook scale training, you typically do only one pass on the dataset. And so you don't do several epochs, but each image is only seen once. So you have like an unlimited amount of data. And a method like dcluster v2 cannot work because it requires several passes on the dataset in order to update the cluster assignment and the centroids. However, it has a tractable learning objective, which makes it more practical and lead to faster convergence. So based on these like observations, we have proposed SwAV recently. So like in one sentence, the main idea of SwAV is to train an embedding with consistent cluster assignments between the different views distortion of the same image. And so intuitively, what we want to do is to find clusters in the dataset and that all the distortion, transformation, crops, views of the image end up in the same clusters. So the cluster should be invariant to the data transformations.
So when you say the views of the same image, it's that same idea of taking an image and then applying like a stochastic data augmentation pipeline to it and sampling multiple times from it. Have you considered doing more than 2 views of an image?
Yes. So that's actually one of our contributions is to instead of having like typically 2 views for one image, we use like an ensemble of views, like for example 6 views, and we see that it increases a lot the performance of the model.
And do you see any relationship between like what transforms perform better or not? Like if all those 6 views were not random crops, for example, would that make a difference? Or if they didn't have jitter or something like that?
Yes, definitely. So in all these kind of approaches, so clustering, contrastive, what you do is really you learn invariance to data augmentation, and that's really the main idea of this self-supervised learning. And so what drives their performance is the data augmentation that you use. And if you don't use the right data augmentation, you will lose a lot of performance. So in the SimCLR paper, they did like a thorough ablation of like what data augmentation are useful for like a downstream task, such as the classification and ImageNet. And so what we did is that we basically took exactly their pipeline and we did not try to optimize it further. But it was like, I think it's a really well optimized pipeline already. But yes, of course, if you want, for example, to apply this kind of approaches to, I don't know, satellite images or medical images, you will have to rethink the data augmentation pipeline to adapt it to your domain.
Yeah, that's a good point. So I guess, would you say that maybe the data augmentation pipeline is very specific to ImageNet or like the types of data sets that we're using?
Yes, I think so, definitely. So maybe not ImageNet, like just ImageNet, but natural looking images like a data set, which, like for example, we have been testing it on Instagram, and Instagram is like, the content of Instagram is very different from ImageNet. You know, if you take like 1 million images randomly from Instagram, it's not going to look like ImageNet at all. You will have like a lot of images of baseball and not a lot of images of, I don't know, monkeys. And I think the pipeline that we're using is really well tuned for like classification and natural looking images, and that might not be the best for like something that is completely different. So to come back to SwAV, so intuitively, SwAV compares the features of different views of the same image using the intermediate cluster assignments. So if the different features capture the same information, it should be possible to predict the assignment of one view from the other one. So now I'm going to give a bit more detail about SwAV. So SwAV is for swapping assignment between views. And so here we take one image, and once again we take 2. So here I say 2 for the sake of simplicity, but as we said before, you can take like much more views if you want. So we take 2 crops of this image, and we take the we look at the feature representation of these two crops on the unit sphere. And now what we do is that we cluster each view of the same image to a cluster of images. And actually, these assignments are done independently, and they may not match. So for example, here, the orange arrow and the green arrow do not match. So for example, the black and white crop framed in green could be a match with a cluster that contains some dog images, while the orange crop could be a match with a cluster that contains different dog images. So what we do is that we constrain the two cluster assignments to match over time. So the system eventually will discover that all the images of dog represent the same information. And so this is done by swapping the assignment. And so it means that we predict the cluster of one version of the image with the other version.
So so to cluster, you need like a target now. So what are those targets?
So the goal of the cluster assignment is to assign B samples to K clusters. So the B samples, they are like the B feature representations which are present in the batch. So these are like a feature representation from the different images of the batch. And the K clusters, they are like K centroid prototypes, which are learned along with the network weights. So the prototypes are learned during training. And so our goal is to assign these samples to the clusters. So it means that we want to find the mapping between the samples and the cluster. And this mapping, this assignment, we can call it a code, and it's represented by this matrix Q. So in the case of hard assignment, where like one sample is assigned to only one cluster, it means that these Q are basically one-hot vectors. And so here it's very important to add a constraint to this assignment. And the constraint is that all prototypes are selected the same amount of time. Because if you think about it, if we do not add the constraint, there is a trivial solution to our problem, is that every samples are assigned to only one cluster, and then it's super easy to predict this cluster because it's the only one.
So can I ask, what inspired this cluster idea?
So there is the SimCLR paper, which came out like at the beginning of the year. And it's really a good paper. And there are many improvements which are orthogonal to the contrastive loss. Like, for example, the longer training schedule, the data augmentation pipeline, the fact of using a temperature in the loss. And all of these improvements, they are like great, but they are orthogonal to the contrastive loss. So we thought, can we leverage these improvements into deep cluster, which was our previous work? And so we tried that, and we found out that it worked like almost out of the box. That's why that's our method, deep cluster v2, where we like the major technical contribution compared to deep cluster is the use of centroid. But apart from that, it works really out of the box with the SimCLR improvements. But the thing is, in deep cluster v2, it's not an online method because you do you have the feature of the whole data set, and then you cluster this, so you have the centroid and the cluster assignment for the whole data set. So it requires several passes on the data set to perform. And so like we really wanted to have a method that works online, so we can train it on Instagram data and the billion scale data set. And so for this, we wanted to have this cluster assignment step, but at the batch level. And that's how we came out with it. So we thought instead of having the centroids, we can have like prototypes vectors that are learned with SGD. And then the cluster assignment, like when you do it with K-mean, you just take the closest centroid, you just assign the closest centroid. But here we found that if we do that naively, then the problem collapses. And so we had to find a solution to prevent the collapse. And so for this, we took inspiration from the work CELA of Asano et al., which was published at iClear 2019, to use optimal transport to incorporate this equipartition constraint that prevent the collapsing. So about the constraint, when you write it in math, it's this set. So the code, the assignment should be in this set of matrices. So it looks complicated, but it's just that all the prototypes are selected the same amount of time. And so now we need to find the criterion for how we decide which samples are assigned to which prototypes, so to which clusters. And so to do so, we use a cost matrix, which is given by the opposite of the dot products between the samples and the cluster prototypes. And so here the cost matrix will give us the cost that we're going to pay when we assign a sample to a certain cluster. And what we want to do is simply to minimize this cost. So to be more precise, if we take the sample Zden and we have this cost matrix, we see that we are going to pay a high cost if we assign it to cluster 1. So here depicted in red. But on the other hand, we're going to pay a low cost when assigning it to cluster small k and big K. So to recap, our goal is to assign the B samples of the batch to the K cluster prototypes with an equipartition constraint, and we follow a cost matrix to do so. So if we write it in math, we want to maximize this problem. And if you're familiar with optimal transport, you will find that this is exactly an instance of an optimal transport problem. And so there is an algorithm to solve this problem, which is Sinkhorn-Knopp algorithm. And the solution is given with this formula. And here U and V are normalization vectors that we can compute with a few normalization matrices. So it's very quick to compute on GPUs.
Yeah, so when we trained SwAV on STL10, we found that it was really fast compared to Sinclair. Do you have any intuition as to why that would be the case?
So what we observed was like within 10 or 15 epochs, we were already above 70% on STL10.
Yes, so you mean it converges faster. So
yeah.
I mean, it's the intuition that we had. It's what I was saying at the beginning of the talk is that SimCLR and all these contrastive methods, they are good, but they need really a lot of epochs to converge because you approximate an objective because you don't have basically access to the whole data set and you only sample a few negatives at each iteration. But in our approach and in the clustering based approaches, you have a tractable objective. And what I mean is that the prototypes that you get, they are kind of representative of the whole data set. So that's why we're hoping that it converges faster, and it's what we have observed empirically.
And we talked about labels kind of adding this bias. Are these clusters, I assume they go beyond just the one object in that image. So these clusters may not be interpretable.
Yes.
Is that right?
So that was for the cluster assignment part. So yeah, in the previous work, so in deep cluster, for example, we what we did is to look at the normalized mutual information, so which is a measure of correlation between the clusters that we get and the real clusters of the dataset. And we were observing that the clusters were more and more similar to the ImageNet labels, but they were not completely aligned with them neither. So yeah, I mean, it's kind of a difficult question also how to evaluate these clusters.
I do have another question. So the constraint that you had for the Q matrix, the equal probability of getting assigned to each cluster, is that for the batch or is it for the whole data set? Because I think in the original ImageNet training, you have a batch size of 4096 and 3072. So, I mean, yeah, by simple pigeonhole principle, it's not exact 1:1 mapping or anything, right?
Yes, so so to answer your question, the constraint is at the batch level. And that's why when we are using a small batch, and for example, if the batch is much smaller than the number of prototypes, what you want to do is to use like a queue, which is composed of the previous batches, in order to like improve your assignment, to do your assignment on more examples. So now that we have talked about the cluster assignment part, we can focus on the cluster prediction loss. So the actual loss which is used to train the network. So we have a feature representation ZT. And so the goal from ZT is to predict the cluster prototype which was assigned to ZS, which is CS. And so we do so with a cross-entropy softmax loss, like on the dot products between the feature representation and the prototypes. So it's really like a basic loss. And so we use the same loss the other way around. So when predicting the cluster prototype CT from the feature representation ZS. It's a loss that is very similar to contrastive learning, but the thing is here you do not have to approximate the denominator, because the denominator like just like the dot products with the whole prototypes. We are kind of summarizing the data set. I mean, it's very hand-wavy, but we're kind of summarizing the data set with the help of the prototypes.
Yeah, I was going to say this is very clever because it is contrastive learning, except you're contrasting on the clusters and not the whole data set, as you said.
Yes.
So it is tractable. How do you set the number of clusters?
So we basically try different number of clusters and we pick the best one. And what was working the best for ImageNet was to use 3,000 clusters. We have an ablation in the paper for the number of clusters, and I found that it was not very sensitive to this parameter, and you can like use smaller or higher number of clusters, and you do not lose much performance.
So if people were just going to try this on their own data sets, do you have a general heuristic as to what the cluster size should be?
Like I would say 10 times bigger, like one order of magnitude bigger than the real number of classes. It's not an exact science, so you should try and see.
With STL10, what we found was we tried out 128, 256, and 512 as the number of clusters. The training was much more unstable for 128 and 256, and most of the runs of 512 converged to a decent score without the queue or without anything.
Okay. And so, yes, some of the advantages of our formulation is that you do not need to use a large memory bank. It works on small and large batches. So given that for small batches, you can use the previous computation, the previous batches to improve your cluster assignment part. And as it's an online method, it scales to unlimited data, so we can train it on billions of images.
I mean, it's interesting to think about the clusters. I wonder if, as the model trains and starts kind of converging, if you grow the number of clusters, if it can get more detailed representations, I guess.
Yes, I think it's a very good point, and we didn't try that. That would be an interesting follow-up. But in addition to our online clustering-based approach for self-supervised learning, we also proposed a new data augmentation pipeline, which is multi-crop. And here what we do is that the previous approaches that take 2 crops from one image, here we take more crops, so for example, 8 crops from one image. And and in order to keep the computational budget low for this, we simply downsize the images.
So this reminds me a lot of CPC, but I guess CPC took overlapping patches, yes. Whereas here you don't necessarily force like a structure like that. You just kind of sample at random still, right?
Yes, exactly. So it was actually inspired from the Jigsaw paper, these small crops, which inspired the CPC. So it's all a bit the same idea. So here what we do is that we take random tiles in the image. As we're dealing with small images, we only consider small part of the image. What I mean is that we don't want to have the whole image which is downsized to a small crop. Okay, so for example, for the image of a dog, in the small crop, you don't want to have the whole dog. You just want to have one ear or just the nose, for example.
Was using small crops just due to computational cost, or was it based on the intuition that an image is composed of like, and any image is like a sum of its parts? So you're also trying to, yeah.
So it's like both your proposition. So it's because you want to map small parts to like a more global view, and it's also because it has the advantage of having a low computational overhead. And so here are some results with multi-crop. So as it's orthogonal to the loss, you can apply it to different self-supervised approaches. And here we look at the performance of like using only 224 by 224 crops on SimCLR, Deep Cluster V2, and SwAV. And we see that we can improve the performance on all these three methods by using multi-crop with 160 by 160 crops and 496 by 96 crops. And so also we observe that the improvement is better for the clustering-based approaches than for the contrastive approach that we consider. But there is also like more than 2% of improvement on SimCLR. We found that it's kind of a generic approach, and we hope that other researchers might want to use it on their own approaches to boost their performance. Yes, so now I'm going to show like very briefly some of the results that we got with the SwAV pre-training. So here we're looking at the ImageNet classification benchmark for self-supervised learning. And here the pipeline is to pre-train ResNet 50 on ImageNet without labels, and then to freeze the weights of the network, the weights of the backbone, and to only train a linear classifier on top of the ConvNet.
How big is that classifier? Is that 1024?
So the classifier is 2048 times 1000. So it's basically like the layer that you put after the global average pooling at the end of your network, and then it has like a dimension of output dimension of 1000 because you have 1000 classes. So it's just one layer. And in green, it's the performance of supervised training on ImageNet. And in blue, it's the performance of SimCLR after 1000 epochs of training, which is which lasts for 40 hours based on our implementation, which is on 64 GPUs. And so we've seen that SwAV converges much faster because we reach better performance after only 100 epochs, which lasts for 6 hours of training. And now what we can do is simply to train SwAV for longer. So we trained it during 800 epochs, which lasts 50 hours based on our implementation. And now we reach a bit more than 75 top one accuracy on ImageNet. Here we can compare SimCLR and SwAV because we implemented it in the same code base with the same tricks. Like we use the mixed precision for the two. So we have really the same hardware. So this was for the evaluation on ImageNet. But this benchmark has not real application in practice, and it's here mainly to compare the different self-supervised methods. And what is more important, in my opinion, is to evaluate the ability of the unsupervised features to transfer to downstream tasks, which is much more useful in practice. So here we compare the SwAV unsupervised features with the standard ImageNet labeled pre-trained backbone on different downstream tasks. So on the left, we look at scene classification on places 205. In the middle, it's fine-grained classification on eNaturalist. And on the right, it's object detection with faster RCNN on Pascal VOC.
Could you talk about the fine-tuning protocol for this?
For places and eNaturalist, we did not fine-tune. We trained a linear classification layer on top of the frozen representations. But actually, we also did fine-tuning experiments on this data set, but we did not put them in the paper. because we did it after the submission. So these results are without fine-tuning. And for faster RCNN, we do fine-tuning of the network for object detection.
So for both methods, this is supervised and SwAV, you just freeze the backbones and then just put in a 2048 unit MLP with the output of number of classes or whatever you're trying to do. And then that's it. And then you train that until completion.
Yeah, but it's not a MLP. I mean, it's a MLP with one layer. So it's just a linear layer. So we see that on all the considered transfer tasks, our SwAV features outperform the supervised backbone. And we are actually the first self-supervised method to outperform the supervised features on this on all of these downstream tasks. So we have released our model and our weights so that other researchers might also benefit by replacing the ImageNet backbone with our network. So that's it. Thank you very much for your attention and for your questions. So the code for this work and for reproducing the results of the paper is publicly available. Also, if you want to find out more details about our method, you can read the blog post and read the paper. And also you can reach out directly to me at mathilde@fb.com. Yeah, thank you.
So yeah, thank you so much for joining us for this presentation. We'll cover the bolts implementation and other things after this.